Okay, this week we're going to talk a little bit more about wind. Really, we're just going to begin to move the air around. We have been discussing about things that may cause the air to move. Now we're going to start putting air in motion so the weather can occur. So, what forces control this? Well, wind is just local motion of air. So, if you're walking outside and the wind hits you in the face, there's some air motion towards you. Or if the wind's pushing you along, coming from the other direction. But what put that air in motion? Well, Newton said that if you don't have something pushing on an object, it's not going to move. It's going to stay still. So there must be some force. And what is force? Well, it's a mass. So how many molecules, how much of an object or air parcel is times its acceleration. So an acceleration is when it's picking up speed, like if you put your foot on the gas. So that's what a force is. The two times each other. So there must be some forces acting on the air to make that air parcel move. Otherwise, it wouldn't move anywhere. It would just sit there. So the greatest force that's available to air is pressure gradient. We know the atmosphere is always trying to get rid of low pressures and diminish high pressures. So the air is always going to flow from high pressure to low pressure. So if there's a very tight pressure gradient, the lines are real close together, then it's like you're going down a very steep slope. So the air is really flowing down that way. The lines are further apart, the less slope, the less pressure gradient. So the more pressure gradient, the more the force can be applied. The less pressure gradient, the less force. If you look at a hurricane, what you find is isobars that are extremely tightly packed together in a very short distance, making very steep slopes. Another force, centripetal force, when you do what this lady is doing with the ball here, fooling it around in a circle, or when you're driving around a curve in the car, what keeps you in your lane? What keeps you going around the curve and not going straight? It's centripetal force. It's what causes the air to move in a circle. So it's another force. It's not independent. Another force is Coriolis effect. This is a weird one. It occurs because the Earth rotates. Think about it. If you're at the North Pole in 24 hours, you really don't move at all, do you? The air is rotated, but you haven't moved. So what about down over the U.S.? Well, one time it's here. We know the Earth rotates to the east. Well, a little bit later, it's going to be over here. Hold it. That was a motion. So there's a force that's generated by the Earth moving called the Coriolis effect. It acts to the right in the northern hemisphere and acts to the left in the southern hemisphere. So it causes the deflection to the winds. Finally, right down by the surface, we have friction. Think about it. If you're up by Lake Erie or coming across the mountains in West Virginia, man, that mountains are rough, right? So that rough terrain, like the mountains, slows down the wind. Now, if you get away from the mountains, you come down here to my neighborhood and you go out over the ocean, there's no rough terrain. The ocean is pretty flat relative to mountains. So friction goes much less. So the steeper, the more undulating the terrain, the more friction. And there's also some friction the further up in the atmosphere you get called turbulence. It's called eddy motion. It's a lot of what causes you to bounce in an airplane when you're flying. Gravity is the pull down towards the earth of everything. That's why we stay on the earth, because of gravity. The net result of gravity and the earth is there's also a centripetal force. Remember, the earth is rotating. So there's a force, centripetal force, helping to keep you down. Not very big, but it's there. So you have two forces that equal gravity on the earth. The normal gravitation force and the centripetal force, both of which act downward. Both means they do not influence air in the horizontal, only air motions in the vertical. So here is a summary of all the forces that you have. We've talked about each one a little bit. Well, let's start looking at an air parcel that's sitting there in the vertical. Well, we have one heck of a pressure gradient in the vertical. We know that because you think about it. If you're at the surface, it's 1,000 millibars. If you go up to 850 millibars, 150 millibar pressure gradient. That is literally 5,000 feet up, not even a mile. If you went that same way in a horizontal direction, I have never seen that kind of a pressure gradient. So this is a pressure gradient that's wanting to pull the air up and out of here. But because of hydrostatic equilibrium, in other words, gravity, centripetal force pulling the air back down towards the earth, that air parcel will reach equilibrium so that it's not going to move up or down unless, say, that air parcel hit a mountain. The mountain might push it up, or it come down the other side of the mountain might push it down. But it will move at a constant rate. That's one of the neat things about hydrostatic equilibrium is that everything moves at a steady rate. It's not accelerating. Now, meteorologists like to simplify wind, so we want to worry about straight wind first. Straight wind is basically a geostrophic wind. It is a balance between the pressure gradient and the Coriolis effect. So what happens as the pressure gradient starts an air parcel moving towards low pressure? Well, that's going to create a velocity in this direction. However, because of that, Coriolis effect is going to begin to take effect. And instead of going just straight down towards the low, it's going to begin to curve. Oh, yeah. And that Coriolis force eventually is going to balance the pressure gradient force. And you're going to get air moving right along the pressure lines. That's geostrophic wind. Two forces, pressure gradient and Coriolis. Horizontal wind. Gradient wind, on the other hand, is very different. It moves in a circle. So around high pressure, you've added another force, centripetal force. So instead of being all in a straight line, that centripetal force makes it out of whack and pulls it in. Oh, it keeps it in a circle. Friction adds another component. Friction will slow down the wind. So if it's slowing down the wind, that's slowing down the Coriolis effect, so that instead of balanced flow from high pressure to low pressure, along between equally right along the isobars, the pressure gradient is actually stronger than the Coriolis effect, so you wind up with more wind inward towards low pressure. Now that is why the air moves towards low pressure and away from high pressure, some at the surface. And you can see that depicted right here. Okay, if you have that, then think about it. If you have winds at the high pressure at the surface that are divergent, well, you're going to have air wanting to sink down into that area, so you're probably winding up with convergent air aloft. So in other words, if you have convergence started aloft, then you wind up with divergence at the surface. So there's a continuity here. When you see winds moving apart at the surface, you probably have convergence aloft. When you see winds moving together at the surface or converging, you probably have divergence aloft. And here you can see it again. Think about it, with divergence aloft is when you're going to get the low pressure systems because you're causing the air to rise. Well, if air is rising, we know it cools. We've already learned that. It's going to reach saturation vapor pressure. Precipitation is going to occur. That's why you have the bad weather with low pressure systems. And here you can see, say you have a lake effect, or in my case, even sometimes a river effect, where you have a smooth wind coming across the lake. All of a sudden it hits the rough surface. It slows down. You get convergence. All of a sudden the air begins to rise, forms clouds, maybe even some showers or thunderstorms. Lake Erie does this as well, coming down off the lake there, winds blowing across it, picking up water. They begin to slow as they reach the land. Convergence develops, helps to push the air up. Oh yeah, you get the heated air maybe more over the land, so you wind up with some convection. That's where you get your lake effect snows. So with that, let's go look at a couple things here I wanted to show you. Here is the current weather map, and there's low pressure north of Lake Huron and Lake Ontario, excuse me. Uh, Notice the wind flowing in towards it at the surface. And if you look out over the water, the wind is stronger over the water than it is over land. So there's less friction, stronger wind over water, slowing as it comes into the land, and the winds are rotating in. Oh yeah, you can even see it on the lakes. You can see there's 25 knot winds here. When you get into the land, there's only 5 to 10. So, and you have some convergence across the lake here, which might actually be causing a few clouds or even a few sprinkles here. So this is just looking at the surface. Now the surface doesn't always look the same as above. Here we have geostrophic winds parallel to it. And that low was about right in this area right here, just a little bit to the east of where this low is. And here you have your winds around the centripetal or gradient wind. And you can see all the winds out of the northwest on this side, coming up from the Gulf of Mexico and the Atlantic Ocean on this side. Finally, when you look way aloft, you don't see the circulation as much, but you see a wavy pattern here. Very strong jet. Guess where the divergence is? Right here with the yellow. If you look back in that same area at the surface, there's the low. So in this case, your convergence at the surface matched up with the divergence along. So if you have any questions about that, don't hesitate to ask. I hope you have a good week.